Okay. So we can explain reflection of light on the basis of Huygens wave theory. So here you can see a reflecting surface, for example, a mirror, reflecting surface. All surfaces reflect light, but certain surfaces are very good reflectors of light. See, we are able to see things because that object is reflecting light to our eye. So we know all objects reflect light, but the amount of light it reflects will be different. Mirror, is a very good reflector. So all objects are reflecting light. When light fall on it, it will be reflected back, obeying the law of reflection. So here you can see a surface xy. What happened now? Only in your class it happens. I don't know why. Not Okay. XY, I think you are seeing. XY is the reflecting surface. AB, see AB is the plane wavefront incident on it. Wavefront, I told you, wavefront. What is wavefront? Is the continuous locus of all the particles of the medium which are vibrating in same phase. All the particles of the medium will vibrate in same phase. Yeah. So such points are when we join, we get a wavefront. Here I have taken a plane wavefront AB. AB is a plane wavefront. And here the rays of light are drawn perpendicular to it. The rays of light are drawn perpendicular to it. Blue lines, that is the rays of light. Red one, that is the plane wavefront AB. See, it is already, you see that wavefront A part of the wavefront already touches the surface XY. And here we know when we are introducing the idea of waves. So we are discussing about waves. So when a wave front touches on it, that also will be reflected. Wave also will be reflected, just like rays. Wave also will be reflected. And here, by the time the wave from B reaches the surface, by the time the wave from B reaches B dash, that means on the surface, this is the surface. So by the time the wave from B reaches B dash, the wave from A also reaches, after reflection, it reaches a certain distance. How much distance it will travel? We know c is the velocity of light, and by time taken by the wave to reach from B to B dash, suppose we can take it delta t is the time for that. Delta t, time interval, we take delta t. So by the time the wave from B reaches B dash, suppose that time is delta t, how much distance this reflected wave move? Because this is the same medium, air medium, no change in medium. So it will also cover the same distance c into delta t, velocity into time. So by the time B reaches B dash, the reflected wave from A reaches a distance A dash, so that A dash is equal to B dash. Both will cover the same distance in same time. So we can take B dash equal to A dash equal to C into delta t. Velocity into time, that will give distance. So distance traveled by light in a time delta t, c into delta t. So in a suppose the waves from B reaches B dash in a time delta t, the distance covered is c into delta t. Similarly, the wave from A reaches A dash at the same time. So B dash equal to A dash. Okay. Now, so this wave's position we got. This wave already reached here. By that time, the wave from A reached here. So in order to find the position of secondary wavefront, with A as center and A dash as radius, you draw an arc. with A as center and A as radius. A dash, how we have to find out? How much distance the wave from B taken to reach the point B dash. Same distance the reflected wave also will cover. Same distance. So with A as center and A dash as radius, A dash as radius, draw an arc. Arc is drawn. Draw an arc. Then you draw a tangent. We already reached here. So these particles will be vibrating in same phase. By the same time, the wave front. See, this is the incident wave front. And in the same time, we get the reflected wave front. It will cover the same distance. So join that or draw a tangent. So Huygens principle is that drawing a tangent forward direction will give the position of the secondary wave front. So you have to draw a tangent from B dash to this arc. So we get B dash A dash, that is the reflected wave front. So this is the way to draw the reflected wave front. Okay. Then we have to prove the law of reflection. Angle I equal to angle R. That we have to prove. We show these angles. So this is the incident ray and this is the normal drawn. Incident ray and normal angle of incidence. And we know the rays of light are always perpendicular to the wavefront. Whenever you draw rays of light to the wavefront, they must be perpendicular. That is the property of the wavefront. So rays of light are always perpendicular to the wavefront. AB is the wavefront. And a normal and this ray of light incident, that's angle of incidence. And here, you know, these are perpendicular. Wave front and ray of light is perpendicular. So this is I, the remaining angle will be 90 minus I. Remaining this angle will be 90 minus I. And one more thing we know, this is a normal and this is the surface. Surface. This is the normal onto the surface, 90 degree. This is 90 degree. And when this is 90 degree, this is, we already got this one is 90 minus I. So what will be the remaining angle wave front with the surface? That will be I, angle I. Because here you know normal and the surface make an angle 90. This is already 90 minus I and this will be 90. Then only total angle will be 90 degree. So this is I, angle I. Similarly, R also you have to mark here. This is the reflected ray. Always when you draw these rays, draw perpendiculars, and you know there is no bending at all because medium is not changing. So you should not bend the rays. Understand? So medium is not changing. So it moves in straight line. So this is reflected ray and normal. I have drawn a normal here. B dash and dash is the normal. And the angle between reflected ray and normal, that is angle R, angle of reflection. And then this will be 90 minus R because wavefront is perpendicular to the rays of light. So this will be 90 minus R. And as we have done before, normal and the surface is making, what angle it make? Normal and the surface make 90. This is 90 minus R. So this will be R. So in this triangle A dash, B dash, we have marked angle I and R. And we have to prove that angle I equal to angle R. We have to prove that I is marked in this triangle A, B, B dash. And R is marked in this triangle A dash, B dash. R is marked. And we have to prove angle I equal to angle R. And we know when you take these two similar triangles, A, B, B dash and A dash, B dash. How can you prove they are similar triangles? You can see here. See A, B dash, that is common to both triangles. A, B dash is common to both the triangles. Then this is 90 degree. This angle is 90 degree. Angle B is 90 degree. And this angle A dash See, this angle is also 90 degree. A dash, B dash, this is also 90. And so we got two conditions, which are they? One side is common and one angle also there, same 90 degree. And if one more condition is satisfied, we can say these two triangles are similar triangles. Which will be that? This one. A dash we have taken. A dash is same as B dash. A dash is same as B dash. Light travels in the same medium, in the same distance it travels, same time. Same time it will travel same distance, light. So we can take in a time delta t, A reached A dash and B, the wave from B reached B dash. So that distance is also same. So two side and one angles are same. So their two triangles are similar triangles. So we can prove that therefore angle I is equal to angle R. We can prove. Therefore angle I equal to angle R, which is the law of reflection. So hence we can prove the law of reflection with this. Okay. So it is the proof. If anybody have doubt, you can call me. Next is refraction, how it is proved. Explanation of refraction on the basis of Huygens principle. So Huygens explained using Huygens principle, reflection and refraction, and is explained wave theory of light. Similarly, other phenomena like interference, diffraction, they can be explained only with the help of wave theory of light. But reflection and refraction, it can be explained with the corpuscular theory and the wave theory. Corpuscular theory means particle nature of light. Here this is Huygens theory means wave theory of light. So light can move as particles and wave. Light can move as particles and wave. Dual nature. Dual nature. So explanation of refraction on the basis of Huygens theory we can see. Here you can see the wave front. AB is the plane wave front incident on the refracting surface. This is the refractive denser media. This is the rarer media. For example, rarer air you can take, and a denser you can take glass or water like that you can take. And here a wave front is incident. Wave front. Wave front means continuous locus of all the particles of the medium which are vibrating in same phase. So all the particles here on this line will be vibrating in same phase. So by the time, and always draw these rays of light perpendicular to the wave front. So B already touched the surface. So refraction takes place. And refraction we know when light ray passes from rarer to denser medium, it bends towards the normal. That we have studied. Wave also like that. Wave also behave like that. When it passes from a rarer medium to denser medium, it bends towards the normal. So you have to draw the wave in this bending towards the normal. Okay, how much distance? That we have to calculate. How much distance it travel? By say time, we are taking the time. By the time the wave from A reaches A dash. By the time the wave from A reaches A dash, how much distance the wave from B reaches? Then the after particles will vibrate in same phase. At the same time, how much distance it travel in a denser medium? Will it travel same distance in a denser medium light? Is it possible for light to travel with the same speed as in air or vacuum in a denser medium? I'll ask you to Michal. Vishal, are you there? No. Vishal won't be there. Then Adityan. Aditya, very simple question. Ray optics and all studied. Then I asked a very simple question. Why you are not answering? Adityan.
Just
Aditya, will light travel with the same speed in a denser medium?
No.
When will it travel less distance or more distance? Denser medium? Will
Less
it
distance.
less distance because it is a denser, so it cannot travel with the same speed as in a rarer medium. Okay, very correct answer. Okay. It taking so much time in a denser medium. Light travels with a less speed than in air or vacuum. So, and for example, for us also, suppose here on the road it is easy to walk, but we know when there is if it is a river, to cross that river by walking, we find very difficult. Our speed automatically decreases. Just like that, the light also. See, when the medium become denser, light find it very difficult to move. So it cover less distance. By the time the wave from A reaches A dash, it cannot travel the same distance as we have seen in reflection. Light cannot travel same distance A dash in the denser medium. It travel a distance A dash by its refractive index. A dash by the refractive index of the medium. So that much distance only it can travel. So BB dash equal to what? A dash by refractive index of this medium. For example, glass. If it is water, we have to divide by the refractive index of water 1.3. If it is glass, we have to divide that distance by glass, 1.5 glass into 1.6 in the glass into 5 glass. Divided by the refractive index. This distance divided by the refractive index. ഇത്രയും ഡിസ്റ്റൻസ് ഇത് ഡെൻസർ മീഡിയത്തിൽ പോകാൻ പറ്റുള്ളൂ. അപ്പൊ വിത്ത് ഹൗ വിൽ യു ഡ്രോ ദ ആർക്ക് ഹിയർ ടു ഫൈൻഡ് ദ പൊസിഷൻ ഓഫ് സെക്കൻഡറി വേവ് ഫ്രണ്ട് വിത്ത് എ ബി as center and BB dash as radius. BB dash, how will you decide? It is a dash by N. With a BB dash as radius, draw an arc. Now you draw a tangent. Tangent. See, A already reached here. Time taken, net time delta, for example. And where will B reach? For finding that, we have drawn the arc and you draw a tangent to it. Draw a tangent to the arc. That will give the position of the secondary wave front or the refracted wave front. You see, you can see they are not parallel because here it cover a less distance. It bend when you draw figure, all these things you must be careful. It bend here. See, it's bending here. This is bending here, bending towards the normal. That you should show. And one more thing, we are not extending the same line here. It is bending. And bend, you see, bend the same angle. With same angle it is bent. And this, you see that the rays are perpendicular. So these are all things that you have to be careful when you draw figure. You see, these rays are perpendicular to the wave front. These rays here and here also you can see the rays are perpendicular. After refraction also the rays are perpendicular, and here the bending takes place. So all those things you have to be careful. And here we have to prove Snell's law. In order to explain refraction on the basis of Huygens principle, we are proving the Snell's law of refraction. What is Snell's law? Sin I by sin R equal to N, refractive index of the medium. So that we have to prove. So for that you have to mark the angle I and R. So I you can mark first. This is the incident ray. This is the normal drawn, and the normal and the incident ray make an angle I. That is angle of incidence. And wavefront is perpendicular to the rays of light. So this angle will be 90 minus I, as we have done before. Here, this is the surface, refracting surface, and that is making an angle 90 degree with the normal. So that angle, if this is 90 minus I, this will be I, because total, you add this total 90 minus I plus I. So that will be 9. This will be, so this angle, total angle is 90, If this is 90 minus I, the remaining angle will be I, as we have done in the reflection case. But refraction also you have to do. This is the refracted ray, and this is the normal drawn at the point of incidence, and the angle between that is r plus r. And this is perpendicular to the rays of light, so this will be 90 minus r. And here this is the normal drawn to the surface, so this will be total angle is 90, and this if this is 90 minus r, the remaining angle will be r. Now we have marked I and r. Reflection also we have done that, I and r marked, and we proved I equal to r. Here we are not proving we will never be equal, I will never be equal to r. So here we have to prove Snell's law. Sin I by sin r equal to n. That is what we have to prove here. Sin I you have to take from this triangle A, B, A dash triangle. What is sin I? This is hypotenuse side. This is 90, this is 90. Opposite to that, that will be the hypotenuse side. So sin I, opposite side, A dash by hypotenuse, B, A dash. Okay. Then sin r you have to take. Sin r, opposite side, B dash by hypotenuse. This is 90 degrees. So hypotenuse is A dash. Then you have to divide sin I by sin r. Next page it is now. Sin I is found, sin r is found, then you just divided it, and B A dash and B dash cancel, and we get A dash by B dash, and B dash we know it is A dash by n. We have drawn the arc with B dash as radius, and what length we have taken? B dash equal to A dash by n. So that is substituted here. A dash by n come to the numerator, A dash get cancelled, and we get n. N is the refractive index of the medium. So sin I by sin r we got, and hence the law of refraction also is proved using Huygens principle. Okay. The 2 mark question, draw the figure explanation, and if this proof, Snell's law you have to prove. Okay. Then behavior of a plane wavefront. See, this 1 mark question is asked. When the plane wavefront is incident on a prism, what type of wavefront we are getting? A refracted wavefront. What is the nature of the refracted wavefront? That we have to find out using this. See, you can see a prism, that ABC is a prism, and a wavefront is incident here. See, this is the plane wavefront incident. KB, you can consider KB as the plane wavefront incident on the prism, and you have to draw the rays of light perpendicular to the wavefront, draw the rays of light, and you can see you extend the ray. Here it reaches A. The ray from the wave from K reaches A. By that time, this reaches a certain distance. We cannot say same distance, because this is denser medium. This the ray or the wave from B has to move a longer distance in the prism. So it will find very difficult. It has to move through this denser medium, very difficult. It is for the light to move in a denser medium. So by the time the wave from B reaches C, the wave from K reaches, first it reaches the surface, the point, the tip of the point, almost near to the point, to the tip of that prism. So it is covering a very short distance in this medium. So it can cover that easily, and it can move a longer distance here. Right. So by the time the wave just crosses this, the wave from K travel a distance Ka plus Al. By the time the wave from B cover only this distance, BC only it can cover. By that time, same time it takes, how much time? Suppose in a time delta t, the wave front from K reaches Ka and then Al, Ka plus Al. Ka plus Al by speed of light in air. It is almost, most of the part is in air. Suppose it is at the tip. it bend towards the base of the prism. Rays of light bend towards the base of the prism. So you have to draw bending. Bending you have to show here. Here incident. Then it bend. When it passes through a prism, it bends. So you have to draw like that. And here here you can write up to denser, bend towards the normal. Then again, two bending take place. When light ray passes through a prism, two bendings are taking place. So here you can see uh, by the time the wave from B reaches C, the wave from K travel a distance Ka plus Al. So Ka plus Al by speed of light in air, that is distance by speed, that is the time. Same time it takes. So BC divided by BC is the distance by speed of light in prism. But they will be equal. Ka plus Al by speed of light in air is equal to BC by speed of light in prism. That way it travels. So this is the new wavefront obtained. So you can't draw this parallel to this because here it travel a more distance. Like that only you can draw. The next is that lens, convex lens. 1 mark question. This one is a 1 mark question. So here when a plane wavefront is incident on lens, convex lens. This is a convex lens. Here you see AB is the plane wavefront incident on it. And you can see the green colored one, that is a convex lens. So what happened here? Here all the same thing happened. Here we have drawn the rays of light perpendicular to that. And here what happened? Here it travel a smaller distance in the this lens, smaller distance. Here also smaller distance. But here it travel longer distance. By the time the wave from P1 reaches P2, here it cover a longer distance. So you have to mark another point which is far from that, not just touching. Far from that you have to take a point. Here also far from that you have to take a point here, because the light has to travel a lesser distance in the convex lens. So by the same time it will cover a more distance than this case. Here by the time the wave from P1 reaches P2, here it travel a more distance B to B dash, cover a more distance, and like that you have to draw the wavefront. So that is the reflected wavefront. You see, reflected wavefront is spherical, incident wavefront is plane, but reflected wavefront is spherical. And these are converging wavefront. We know convex lens always converges the rays of light. So here you can see the converging rays. So arrow mark on the rays, and the wavefront will be, the radius will be decreasing. Converging wavefront we are getting. Okay, only 5 minutes. The next case is concave mirror. Again, concave mirror, you can see what is the reflected wavefront obtained from a mirror. Mirror also we are getting a converging wavefront. We know concave mirror converges the rays of light. So AB is the plane wavefront incident on it, and we have to draw the rays perpendicular to that wavefront. And A reaches here, A reaches the point G, it will be reflected. Similarly, the wave from B reaches H, that also will be reflected. But this ray, it has to go a longer path, because here there is a dip here, center part. It has to cover a longer path here. Medium is same, but it is concave in shape. So here this ray reaches first. This will reach later only. So by the time this from the ray or wave from A reaches G and then D, it will cover a smaller distance here only. So you cannot mark them on the same line. Here it cover a lesser distance, because this ray C, the wave from C, has to move a longer distance here, and we get a converging wavefront itself. This will also converge somewhere. Here it will converge. So this is the explanation of the behavior of a plane wavefront in prism, lens, and mirror. 1 mark question usually asked this one. Next is the interference of superposition principle. That also I have sent that video of superposition principle. If you observe that, it will be very easy to superposition principle. Superposition principle last year also we have studied. Here you can see the waves. Waves y1 is the displacement of one wave. Y2 is the displacement of the other wave, black color one. And when these two crusts are superimposing, we get sum of the displacement. This is crust of one wave, this is the crust of second wave, and after superposition, we get maximum displacement, sum of the displacement of the individual waves. So, y displacement of the resultant wave, this displacement of the resultant wave is y1 plus vector sum. You have to take vector sum of y1 and y2. So you please watch that video very well. It is explained there how the superposition is taking place. Please watch at least after the class if you are having such. So time is taken along the x-axis and displacement is taken along the y-axis, and superposition principle is applied here. Two waves are drawn, y1 and y2, and their troughs are taking place at the same time. Troughs, T-R-O-U-G-H. Troughs are taking place at the same time, and the resultant wave will be some constructive superposition is taking place. Constructive superposition. The resultant displacement is sum of the displacement of the individual waves. Here trough, both the trough are taking place at the same time. So the resultant displacement in the downward direction, that is sum of the displacement of the individual vector sum. You have to add vector sum of the displacement of the individual waves. Here also the same thing we can see, but crust and trough are taking place at the same time. See y1, this is red color one, that is one wave. Red color one, that is one wave, and the blue color wave, that is a y2 wave. Two individual waves, y1 and y2, and you can see crest of y1 wave is here, and at the same time, what is happening for the second wave? Its trough is happening at the same time, at the same instant of time. Trough, this is trough, lowermost point, and crest, that is happening.